Show's ready, huh?
Okay, awesome. All right, so a little bit of housekeeping before I get started with my formal introduction. Apologies for not having the posters out. There was just a little bit of a hiccup in that regard, but you'll see in my next emails and around campus those posters, and then I'll have the rack cards here as well for the upcoming lectures. So, welcome to tonight's segment of the Adams State University Faculty Lecture Series. For those of you who don't know who I am Jess Gilardi. I'm professor and director here, and I coordinate the lecture series. So thanks for attending tonight's lecture. Keep an eye out for upcoming lectures. The next lecture will be next Thursday. Dr. Chris Kam of Psychology will be presenting a lecture on what AI cannot do. And it'll be same place, same time next week. So this evening's event is presented by Dr. Matthew Nehring, professor of physics from the School of Science, Technology, Engineering, and Math. Matt Nehring earned his PhD in physics from the University of Colorado at Boulder. He has been teaching classes in physics, astronomy, computer science, and engineering at Adams State for more than 2 decades. He enjoys drinking good coffee, spending time outside year-round with friends and family, and looking through telescopes. And something as a personal privilege because of the succinct introduction, I just want to add a couple of things. That I really do want to share my appreciation for Dr. Nehring. I've known Matt for a handful of years, and we've worked in different capacities, sometimes in challenging situations. I've always respected his thoroughness, being level-headed, and working towards the greater good. And despite my background in studying and at times trying to practice leadership, I have definitely modeled parts of my own approach to leadership after Dr. Nehring. So tonight's lecture is on celebrating 100 years of Galaxies. And in his words, 2024 marks 100 years since galaxies were discovered. This lecture includes a historical account of steps leading to their discovery, important milestones from the past 100 years, discussion of galactic evolution, and of course, lots of beautiful and thought-provoking pictures. So help me in welcoming Dr. Nehring.
Thank you, Jess. Is it possible for us to turn the lights down just a little more? Just because we have some pictures there and they kind of get washed out otherwise. So thank you, Jess, for that longer introduction than I had planned. Jess asked for a bio sketch, and I said, well, I'm of the philosophy that less is more, so I tried to keep it to about 3 sentences. But thank you, that's perfect. I appreciate that. Appreciate the comments there. Before we get started, I would just like to do, I'm going to rewind to the slide for a moment, but if I can get my clicker working, which has been not always great, as some of you know from just the last few moments. Let's swap that out, I guess. Sorry, more delay technology. All right. I hope this will work better. There we go. Okay, so just a couple of things. So I put a QR code up here. Just a quick note, after this program here, starting at 8 o'clock, I'll be out at the observatory. The moon is out, so it'll wash out a lot of things, but the moon is always great to look at. We'll get to see some double stars, maybe a globular cluster, with a little luck, maybe the ring nebula or something like that as well. So if you have a few moments, you don't have to come out from 8 to 9:30. You can come out anytime in that time window there and spend 5 minutes out there and get to see some cool things and then go about your business, so it doesn't have to be a long stay. That is a QR code for the map. If you don't have your QR code enabled phone with you, if you just go north of here, down past Coronado Hall to where the Lutheran school is, there's a path from there out to the observatory, which of course is between the baseball and softball fields because that's where you would put it. It is the darkest place on campus that we could find. So there will be some lighted cones out there, so follow the blinking red lights and you'll find your way out there. So with that, I'm going to rewind here just a little bit back to this slide. So as Jess said in my introduction there, we are looking to celebrate 100 years of Galaxies. It was 100 years ago, 1924, when the first one was discovered, and you might wonder, well, we've got a lot of galaxies. How is it that we lasted so long without actually discovering some galaxies out there? And we will talk about that, and it depends upon what you mean by discovering, right? So we will look at that a little bit. This is an image of M51, also known as the Whirlpool Galaxy. It is a pretty common, I would say, amateur astronomer target and so forth. And we are fortunate in the 21st century here to have really fantastic images at the touch of our fingertips, right? If you subscribe to the astronomy picture of the day, or you just scan through various things on Instagram or on the computer or whatever, you can see some fabulous photographs, right? And so this is an example of one of those. It is really two galaxies, but one dominant here, a spiral galaxy. But up until 1924, it was thought of as a spiral nebula. We didn't know what those things were. So we're going to go through a little bit of a historical perspective on how we came to learn these things. And this is an image of again, M51. So the next few slides are all M51. By the way, if you're wondering why it's called M51, it is the 51st object in the Messier catalog of things. It's actually a catalog of things that Charles Messier put together to say, don't go look at these, quite frankly. And he was a comet hunter, and these things weren't comets, so don't bother looking at them. But it's actually survived for a few hundred years, and it's probably the most common list of things to go see. So it's the 51st object in that collection. And these things almost always have more than one name, so they're in lots of catalogs. The image on the left is also an image of the M51. It is a hand-drawn sketch, so naturalists going back centuries and millennia, quite frankly, used sketches as a way to record the natural world, right? Whether you're talking about plants, or whether you're talking about animals, or you are looking at glaciers, or you are doing landscapes, sketching was really prominent in the natural science world back for several hundred years, and to a certain extent still is, although things like photography and so forth have taken a lot of that skill and touch away. The image on the left here is from a scientist, and he's a French astronomer. His first name is Jean. I wouldn't know how to pronounce his last name, so I'm not really going to attempt to do that. He was associated with the Paris Observatory in the mid-1800s, and he sketched this image. I think it was 1863 or something. It's not the first image that was sketched of the spiral nebula, so to speak, but it gives you some flavor of what it could look like. If we rewind a little bit more, again, this is a sketch of M51. This was done by an engineer and businessman who was an Irishman. He was also known as William Parsons, I think was his name, but he was the 3rd Earl of Rosse. If you care to keep track of what that means, you are better at it than I am. He had a lot of money, though, okay, so that's one thing, and he liked to look up in the sky using telescopes, and he commissioned and built this telescope. It was the largest telescope in the world for probably more than half a century, well into the 20th century. And it is a 72-inch telescope. And you can see from the sketch here that by 72 inches, we're not really referring to the height of this object, because you can see the sense of scale there with people, right? The 72 inches refers to the diameter of whatever light-gathering instrument it is. So the top of that would be 6 feet across. And there's a couple reasons why you wanted telescopes this large. It's a bit of a misnomer to think that you want telescopes so that they can magnify stuff. Magnification does play a role, but there are two really primary roles of a telescope. One of them is just collecting light, right? So turns out there's lots of things in the universe beyond what you can see with the naked eye. You just have to have some object to collect that light and focus it to a place where you can actually see it. And so that's why you want the large diameter, is to collect more light. Your eyeball is limited by the diameter of your pupil. The telescope there is limited by the diameter of the mirror that's collecting it. So one is to collect light, and the second one is to resolve different details in whatever object you're looking at. So the resolution is how close can something be, and you can still separate it into two objects. And so if you look at this image, this is one of the first sketches of M51. And if you compare that to a similarly oriented photograph of M51, you'll see that there's a lot of pretty similar detail, right? And so it was in the mid-1800s that they started calling these things spiral nebula, because you started seeing this spiral shape that was coming out. Now the word nebula has Latin roots. My Latin is not all that great, but it has meanings of fog and mist and smoke and things like that. And so the nebula, when you look at it through a telescope, doesn't look like this thing on the left. Even today, if you're looking at it through a telescope, if we were fortunate enough to see it tonight, it would look more like that, and actually it wouldn't even have as much detail as that. So it looks like a foggy or misty patch, unless you do a time-exposed photograph, for example, and you can get a lot more detail. But mid-1800s, okay, we're calling these things spiral nebula. We don't know what they are. Couple more images. Some of these are photographs and some of them are sketches. So the image on the right there was from a paper, I think 2008 it says, the Journal of Astronomical History and Heritage. And it was a paper talking about some of this history, not a tremendous amount, but I really like this image. So as you're going across that top, the first 4 images up on the top there are 4 different astronomers who were sketching M51, right? And as you can see, partly because I had access to lots of sketches, and partly because M51 is really cool to look at, it shows up a lot in the talk tonight, particularly in these early stretches. The one on the very far right, that is the Frenchman, okay, that 2 slides ago we saw that image there. But as you go across on that top, John Herschel made the sketch, I think in 1833, of M51 on the left. And it's really before the telescopes were large enough to start resolving that spiral structure detail. So you can see some sort of dark bands. The other thing about those sketches is you're kind of sketching in negative, if you want to think of it that way, right? If you're looking through the telescope, you're seeing bright things, but it's hard for you to draw with a bright pencil, right, on a white background. So you sketch it, and it's sort of like a photographic negative, if you will. So the Earl of Rosse, he produced those 2 in the middle there, so 1845 and 1850, and then we go across and keep on going down. Now, I'm just going to let you look at them for a moment there. There's actually 3 images in there that are photographs and they're not sketches. And I don't know if you can tell which ones those are. I've already told you the top 4 are sketches, so you've got a little bit of a head start on that. E, the first one in the middle row on the left, is actually a photograph. And then we have F, G, H. Those are all sketches again. Down on the bottom here, I is a sketch as well. I'm going to jump over J for a moment. K, the second to the last one, is another photograph. And the last one there by Roberts is also a photograph. J is actually a sketch of a photograph. So you take a photograph and then you make a sketch of it. I'm not sure what the rationale was there, but it actually makes for a pretty good comparison. And what you can see is that, well, all right, if someone tells you that that is a photograph, maybe you're saying, yeah, I can see some more detail there. But maybe you wouldn't be surprised to look at those things and say, well, they're probably sketches, right? I mean, it's not super easy to tell the difference. But in the mid-1800s, photography was just coming into being, and it was certainly something that the astronomers were keen to take hold of, right? Instead of having to put your eye up here and sketch details back and forth like this, you could just take a time-exposed photograph, and then you would have that data recorded. So it was really a big advancement. The one on the left here is a photograph. All of these are M51. This was from 1898 through a particular telescope. And so if we then slide into the era of photography, we are still looking at these things as spiral nebula. We don't know what they look like. These are 3 different objects, but the one on the left here is M101. It's also known as the Pinwheel Galaxy, and it is a photograph from 1892, and another one from 2023, just to give you sort of a modern feel of what that might look like through a decent telescope, whatever that means. The telescopes along the top line there are 20 and 24-inch telescopes, so the diameter of those telescopes at that time was something like this. But that middle one in particular, you probably agree, has some pretty good detail in it, right? So when you start actually taking those photographs, and we're talking 1888, that's pretty good detail that you're able to get of that then spiral nebula, so to speak. This middle one is actually the Andromeda Galaxy. You've probably heard of the Andromeda Galaxy before. It is the largest spiral galaxy that is nearest the Milky Way. Over on the right-hand side, those 2 are the Triangulum Galaxy. They are also it is also relatively close to the Milky Way galaxy. In fact, we will see those 2 show up a little bit later when we talk about the Milky Way in a bit more detail. But I just wanted to show you those to sort of say, look, even back in these days, you could get spectacular photographs, right? They weren't in color, so the technology wasn't quite there yet. But the reality is when you take a photograph with a modern telescope, you actually, if you just took a photograph and looked at it on your screen, you wouldn't even see that much. Usually it's almost all black. There's a lot of processing that goes on. You oftentimes end up putting different colored filters in front, and then you blend all of those photographs to get the color that you think that it should really have out there. So it takes a lot of processing to get these final images. So, spiral nebula, what are they? Where are they? Back to the 1888 photograph. In the year 1920, the National Academy of Sciences sponsored what they called they called it the distance scale of the universe, but they were billing it as a debate. And it was a debate between two famous astronomers. They actually had to recruit the astronomers to do this. It wasn't these astronomers were just wanting to go head to head with one another, but they thought it would be really good for their national meeting to have this debate because no one knew what they were, and there were a lot of arguments and a lot of discussion about what these things were. So one side, Harlow Shapley was the person arguing this, and he really believed it. He said that they were just nearby clusters of gas and dust. And by nearby, he meant in the Milky Way, and by the Milky Way, he meant the universe. So at the time, they didn't know there was anything beyond the Milky Way. It was all just, one big pattern of stars and gas and dust and so forth, and everything is relatively nearby. The other perspective was, no, these things are really distant. They're island universes, if you like. So it's sort of like taking the Milky Way. There were folks at the time that said, oh, we have these structures in the universe like the Milky Way, and they're just really far. And it wasn't a debate in the sense that you just had two people going at the debate. They were two separate talks. And at the time, of course, they didn't have email. And they wrote a lot of letters to one another. And they were both very collegial about it. There was some concern about who would go first. And then the second person would go, and there would be no rebuttal. Should they have a rebuttal? And they decided, no, we don't want this back and forth. But the two scientists shared their talks with one another. One of them performed much better than the other. He was a great public speaker. At the time, it was not unusual for someone to give a paper, so to speak, and they would read the paper. So Harlow Shapley wrote a paper, and he stood in front of the audience, and he read the entire paper, right? That was his talk. Whereas the other individual, Heber Curtis, was much more dynamic and free-flowing with his talk, and perhaps a bit more entertaining. But if we really want to solve this, which they wanted to in 1920, you need to know how far away these things are. If you want to know what they are, you better know how far away they are. And so we need to measure distance. And I promise this talk is not going to be too technical, but I do want to give you a little bit of a flavor as to how you go about measuring things in astronomy, because it turns out you can't stretch a tape measure out to the moon, and you certainly can't stretch a tape measure out to other stars and other galaxies, right? And so you have to figure out, how do we measure distance? And in astronomy today, we still have this as a huge problem. They've constructed what's called a distance ladder, and the way you do this is the first rung of the ladder is what you know the best. So you have some technique that you can measure things that are close by, and you calibrate stuff, and then you have another technique that sort of builds on that and can go out a factor of 10 or 100 beyond that. So when the astronomers were first looking at how to measure things, they were looking at things like stars. I've put up a tree there. That's actually an image from one of the astronomy textbooks that I use when I teach astronomy here. But the idea, I think, is a little bit more familiar and easier to imagine here if you're looking at it like this. So let's imagine you want to measure how far away that tree is on the other side of that river, and the river's too swift or too wide or whatever for you to measure. So you get out your surveying equipment, which is basically a telescope, let's face it, and you level it out nicely, but you swing it over here and it's pointing right at that tree. Then you can pick up your telescope or your surveying equipment, or have a second one, and you walk this way for a ways and you put it down. And lo and behold, the angle to that tree has changed, right? If I'm standing over there and Mike is the tree, we're looking in this direction, and then as I come over here, I measure a different angle. And one of the great things about high school trigonometry and geometry is you can use that information along with just stretching a tape measure from here to there. That tells you everything you need to know about that triangle. You can figure out the distances to everything there. So the distance along that dashed line is really what we're going for, right? How far away is that tree? We do the same thing with stars. So in the earliest measurements were sort of 1839. Now for stars, you don't just get to pick up your telescope and walk across the lawn and take a new measurement. You have to wait a little while because you want that baseline to be as large as possible. And the best baseline we have is to go out and take a measurement, say January 1, wait 6 months, and go out and take another measurement June 1, because you're on the opposite side of the sun. So as long as you know that distance, you've got a big distance right there. You measure these angles, which are still small differences, but it gives you the same geometry, and from trigonometry you can figure out the distance. So by the early, mid 1839 or so, they had measured some stars. It was a handful of stars at that time that they measured. And there was a Dutch astronomer, Jacobus, I think, I don't know how you would pronounce it, but Captain, he had a catalog of 385 stars. I mean, imagine that. We know the distance to 385 stars. How fantastic. But that's all we knew, right? And most of them are nearby. And what's worse is they tried to do this for spiral nebula, but they couldn't, right? They kept trying to measure distances, but they wouldn't. And the difficulty there is they're just too far away. Right? So if you don't have a long enough baseline this way, you point your telescope out, it's still at the same location. So they can't measure the distance, they don't know where these things are, and it really struggles. So along come some undersung heroes of astronomy, like some undersung heroes of the rest of the world, shall we say, or unsung heroes. The women in the field of astronomy, they could go study astronomy and get degrees in astronomy in the late 1800s and early 1900s, but they couldn't get a paid position. They weren't allowed to have professorships. They certainly weren't allowed to run an observatory. Sometimes they were allowed to work in observatories, right? Usually for free. But they enjoyed the work and wanted to be doing something, okay? So they would go in, and you see a group here, it looks like 8 women working away at the Harvard Observatory. Quick aside, if you have if you have an interest in the history of astronomy and contributions of women in particular, there's a great book called, by Dava Sobel called The Glass Universe, and it talks about the women of the Harvard Observatory. Really fantastic book, I would highly recommend it. But this group of folks here, and let's see if I wonder if there is a laser on this. Yes, there is. Okay, so this woman here, the third from the left, is Henrietta Swan Leavitt, a great name, I think, by the way. And her interest really was studying variable stars. Well, what's a variable star, you wonder? Well, it's a star that changes its brightness with time. So there's a graph of a variable star, the brightness on the vertical axis and time on the horizontal axis. Unlike our star, which is constant brightness day in, day out, essentially, there's a particular class of stars, actually many classes, but one particular class called Cepheid variable stars, where they really change their brightness significantly. And they're a much bigger star than the sun is. In fact, they might be 30 or 50,000 times brighter than the sun, which means you can really see them from a long way away. But they also go through this cycle where they get really bright and then they get dimmer, and they get really bright and they get dimmer. And it's pretty fascinating how that works. In 1908, she was studying 17 of these Cepheid variable stars, or at least variable stars. She studied 17 of them really intensely. And I had to have an abbreviation there. SMC is for the Small Magellanic Cloud. By the way, that name is changing, but they're probably keeping the initials. I don't know if it's official yet. But the Small Magellanic Cloud, which is a satellite galaxy to the Milky Way galaxy. If you ever go to the southern hemisphere, you can see the Small Magellanic Cloud and the Large Magellanic Cloud with your naked eye. If you see any astrophotography from the southern hemisphere, you will often see those two prominently displayed there. But she was studying those, and in 1912, she did another study of 25 Cepheids in the Small Magellanic Cloud. But in the intervening time, someone had measured the distance to one of the Cepheid variable stars. So these are all over in the Milky Way, all over in other galaxies and so forth. So this particular type of variable star is reasonably common. They are interesting because something weird is happening out there, and we would like to know what, right? So she's studying these things. And someone was able to measure using parallax, that same technique we talked about. They were able to measure the distance to one Cepheid variable. She started studying these things and found, oh, and by the way, one of the things I really love is, seem to have a photograph of a graph like that, right, on the wall there. So not only does it have some great artwork, but they have great artwork that is also a graph of science, which is awesome. At least if you're like me. Promise there's not too many more graphs. This is a graph taken from her 1912 paper, and along the horizontal axis is the period. So think of the period. How long does it take to go through one cycle, right? You go bright, you go dim, you go bright. That's the period that it takes. And it turns out that not all Cepheids have the same period. And then the brightness. She started plotting this thing, so they found lots of them that had this variation, right? And she said, well, I wonder what happens if you were to plot this and say, hey, what does it look like if you have luminosity, or the brightness on the vertical axis, and the period? And lo and behold, there's some clear trend there. The way her data work here is like this first data point and this first data point are from the same star. One is the peak brightness and one is the lowest brightness, okay? and she follows that for 25 that have different periods. So we're going out in this direction longer and longer times, right? So the ones that are doing this, going up and down really quickly, are also pretty dim stars. And the ones that are taking a lot longer to go through this cycle are much brighter stars. So she developed this relationship. Hey, if you can measure the period that it takes, I can tell you how bright that star is, right? So you are doing this type of thing. Alternatively, if you can measure the brightness, you get the other one. But that's not the important part. The important part is someone else measured a distance to one of these stars. So you take that star and you plot it on this graph and you say, aha, oops, sorry, that star, maybe it was right here. It's maybe in this spot right there. Okay, it lands on here. But they know the distance to that one. So these Cepheid variables are different brightnesses. Let me give you a brief analogy to maybe make this a bit more real. If you were to take 50 100-watt light bulbs, and at least half the audience still remembers what a 100-watt light bulb is, so good. Half of you. And if you don't know what a 100-watt light bulb is, talk to someone that's a little older than you. So if you take 50 100-watt light bulbs, okay, and go out on the valley floor in a dark spot, and you have a distance, you're going to put one of these maybe a half a kilometer or a kilometer away from one another. So you plant one here, and you travel a half a kilometer, and you plant another one, and you keep doing that for your 100 light bulbs or whatever you have. You probably would agree that the one that's furthest from you is going to be dimmest, right? And the one that's closest is going to be bright. If you know that they're all 100-watt light bulbs, all you really have to do is measure the brightness of this one and measure the brightness of this one out there, and you can actually determine exactly what that distance is, right? Because you know it's 100 watts. That's the beauty of this, right? So if you can measure the period, then you know the absolute brightness. Now, the absolute brightness is what's important. It's the 100 watts. It's not how bright it appears, like that 10-mile away 100-watt light bulb that you can barely see, right? You still know it's 100 watts. This graph put that on the map. That allows you to then say, aha, I have this Cepheid variable. I know its period because that's easy for me to measure here. Then someone can read off this graph and say, well, here's the absolute brightness. Here's how many watts it is. And as soon as you know how many watts it is, you can easily work out the distance. So it was really spectacular. So we're talking 1912, she was put this together and said, hey, we now are able to measure things out really far, right? So they're measuring things that are 30,000 light years away. And if you've probably heard the term light year before, light year is how far light travels in 1 year, right? So it has a finite speed, but it's a big distance. Okay, so hooray for Henrietta Swan Leavitt. She really transformed what we could do in astronomy and did not get a Nobel Prize for it. She probably should have. And in fact, Edwin Hubble, our next astronomer, there's a story that you can read where he says, really, she should have received a Nobel Prize for that work. It was so important to astronomy. But, of course, was overlooked like lots of other women scientists throughout history and continuing to today. I'm sorry for that. Okay, so Edwin Hubble, you've probably heard of Edwin Hubble before. The Hubble Space Telescope, right, is named after Edwin Hubble, famous astronomer from the early 1900s. He was at the Mount Wilson Observatory observing in October 1923. And the way big research telescopes work is, even back then, you had to put in proposals to say, hey, I want to go study this. Can I have some observing time? You do that on the Hubble Space Telescope. You do that on the James Webb Space Telescope, and so forth. And if your proposal is deemed good enough or worthy enough, they give you some time. So he had 3 days. And on, I think it was the 4th, but I could be wrong. I think it was the 4th. Hey, he was taking a photographic plate, right? So they're doing photography with this. And he is photographing the great nebula in Andromeda, now known as the Andromeda Galaxy, right? So he's photographing this thing, and he notices what he finds to be a nova. So a nova is a star that suddenly appears, right? You've probably heard the term supernova before. We're not thinking supernova here. It's a different type. It is a nova. We think we understand the process for it now, but it's a sudden brightening of a star that then fades, and it's gone for a long time. He thought he'd found a nova. And the nova he found is right between these two little marks. He made those two little marks, and there's a star right in between those. And he said, lo and behold, we have a nova here. So he labeled it with an N. And then he went out the next night, and he took another photographic plate of it, okay? And he's just super excited, and his observing time ends then, right? I mean, he's got 3 days. It's not enough. he doesn't have as much data as he would like, but fortunately, the Andromeda Galaxy is something that had been photographed a lot. Back then, the Andromeda Nebula, right? So it had been photographed a lot, and so he went back into old photographs, and what he found was, lo and behold, it was not a nova, it was a variable star. So you can see that he crossed out on this plate right here, the N, and he put var for variable with an exclamation point, because he was so excited about this. I know we can now determine the distance to this. We have a variable star here, right? Pretty exciting stuff. Pretty amazing stuff that you pick out that star there, right, on this photographic plate. So I'll show you a couple other images of this. This is that same thing, and it's in positive, I guess, instead of negative. Same spot, now you can see that dot, right? Hey, that's really bright, right? So imagine you're looking at this, and more or less real time, right? He gets up the next morning, and he's looking at this plate, and he's like, wow, okay, I found a variable star. I mean, it's not like it was weeks later. He found this variable, or found this nova, which he then figured out was a variable star. Super excited about it. Just to give you a little bit more of the sense of scale, modern picture on the left, the outline that you see here, the big rectangle, is the one on the lower right. That was his, right? So his star is that one right there. If you then blow up this little tiny region that's right there into this, we're looking at that star. So he's picking out this one star and saying, hey, there we go, right? We're going to go measure this thing. I think it's just amazing that you would be able to do that. But I guess if you stare at these plates enough, I mean, they have telescopes these days that are constantly doing all-sky surveys all the time, right? But it is just a computer that takes an image, and you have a computerized algorithm that compares it to the one the night before. And you subtract the two, and you say, oh, yeah, here we go. This thing is a lot brighter. But you didn't have that luxury back then. It was astounding. So this is an image from his notebook. So this is in a letter that he was writing to another astronomer. And he's really excited. I think this is from February of 2024. And he said, well, this is all the data that is giving us this variable star. So all those little points are plotting out. He's plotting brightness, and he's plotting days there, just like those other graphs I was showing you. But he found that this has a period of 31 days, which is a really bright Cepheid star, right? But that 31 days, bam, he can put it up on Henrietta Leavitt's image there, or graph there, and he can figure out, based on that, how bright it actually is, and then from that do a quick calculation and determine how far away it is. And he determines that it is something like 1,000,000 light years away. So up until that time, things were maybe 30,000 light years away. Suddenly this is 1,000,000 light years away. In fact, Henrietta Leavitt Swan had measured the distance to the Small Magellanic Cloud at some level, and he found that this was more than 10 times further away than that. And so it really put to rest the idea that they're inside the Milky Way. They're not part of our neighborhood. They're something else. These things are really island universes. And on November 23rd, 1924, coming up here in a couple months is the anniversary of at least the New York Times announcing this. So on the left there, Dr. Hubble confirms the view that they are island universes similar to our own, that you have these vast expanses of space with nothing in between there. And if you read this, so confirmation of the view that spiral nebulae, which appear in the heavens as whirling clouds, are in reality distant stellar systems or island universes, has been obtained by Dr. Edwin Hubble of the Carnegie Institution's Mount Wilson Observatory through careful observations. The results are striking in their confirmation of the view that these spiral nebulae are distant stellar systems. They are found to be about 10 times as far away as the Small Magellanic Cloud, or a distance of 1,000,000 light years. And in fact, they are not. It is not 1,000,000 light years away. It is more like 2.5 million light years away. Okay, so it's even further than he had originally thought, but it really put to rest the great debate. This was not peer-reviewed, not published yet. Okay, it was just in the newspaper, but a word had gotten around sufficiently that they were all working on these things, and I think it was still a couple of years before he actually published those results. Shifting a little bit from that, so now that we know these things are spiral galaxies, or spiral island universes, if you will, just to give you a little flavor of, in this particular slide, the same galaxy taken by an amateur astronomer and a professional astronomer, so the one on the left and the one on the right. Now the magnification, right, you can magnify anything you want on your computer screen, right? You hit Control plus and boom, it gets bigger and bigger. And eventually the resolution is so bad you can't really tell what you're looking at, right? So it's not all about magnification. The one on the left certainly is more magnified, but notice how much more detail you have in the one on the left, right? one of the things in some of the upcoming photographs that you might want to look for here are these things that have these nice bright spikes on them. All those bright spikes are telling you those are stars, and they're in the foreground. They're stars in the Milky Way. They happen to be aligned up that way. And it's just a fluke of physics, or a feature of physics, if you will, because telescopes need supports coming out for their central mirrors and so forth. It turns out you get these what we call diffraction spikes around there. But it's kind of handy because then you can tell, hey, I'm looking at stars that are nearby. Everything else there is in that distant galaxy. And notice the names there, so it really has the flashy name of NGC 6814. Okay? NGC stands for the New General Catalog. So astronomers really like producing catalogs of interesting things. This is the 6,814th object in that. Imagine that for a little bedtime reading for yourself. So more spiral galaxies, 2 of them here. Okay, same thing, just different photographs. The one on the right there is, I believe, Hubble Space Telescope. It certainly is produced by NASA and the European Space Agency. And there's a lot of processing, like I said before, that goes into producing these beautiful images. The one on the left there, same galaxy, same orientation, maybe a little less detail, right? So probably not quite as big a diameter as the Hubble Space Telescope, plus it's a ground-based telescope. So when you're taking it with a ground-based telescope, you also have to worry about light coming through the atmosphere, which causes it to wave around a little bit and causes it to be more blurry. These are both examples of barred spiral galaxies. So the one on the left is NGC 6217, the one on the right is NGC 1365. And I'm really just trying to give you a few different examples of what types of spiral galaxies there are out there, and in fact just what types of galaxies are out there. So barred spirals are characterized by kind of a big central bar where it's super bright and there's just a tremendous amount of stars in that region. And then you also have these spiral arms coming off. By the way, these spiral arms is where most of the star formation is happening in spiral galaxies. So when you look at those things there, there's a lot of gas and dust in here, which is how you form stars. So the dark regions right there, for example, are clouds of gas and dust. But as they get disturbed, they can collapse and then eventually become a star. There's enough mass there and it ignites and it gets really bright. So that's why you have all of these regions out here as well that have these really large bright stars. Same thing over here. This one's kind of bluish. Blue tends to also indicate a lot of star forming activity. But beautiful photographs. This one was taken just to give you some sense of scale. This one is Hubble. This one is a 1.5 meter telescope, so it's a telescope something like this. The largest telescopes we have down at the observatory, if you come down there tonight, are 20-inch telescopes. So, you know, they're pretty substantial, and you can get pretty good views of a lot of things. Other galaxies, these are lenticular galaxies. They're kind of lens-shaped is how they get their name. If you're like me, you look at that and say, well, that's pretty cool, but it's not like those spiral galaxies. I mean, the spiral galaxies are really beautiful to look at. These things, there are some features in there, right? You have these weird dust lanes here. This thing has a couple of jets coming out of it, but it's kind of a fuzzy patch more so. You know, this is sort of what you might get to see if you're looking at one of those spiral galaxies through an amateur telescope. Even our 20-inch telescopes, you look at it, it's like, it's kind of a fuzzy patch. Or you can look at it and say, wow, I'm looking at something that is 10 million light years away. How fantastic is that?
Matt, at what point did they switch from the nebula language to the galaxy?
Yeah, so shortly after Hubble, they switched to calling them galaxies. So up until then, and part of the reason is because nebula, it turns out there are a lot of other types of nebula. So we have planetary nebula, which, by the way, have nothing to do with planets, but they didn't know that at the time. Astronomy is one of these fields where it has kind of been relatively slow progress, and it has grown up around itself, right? And so there's also, if you think of constellations, we have mythology associated with a lot of the constellations. The astronomers ended up dealing with that with just saying, well, this constellation has nothing to do with these 6 stars, it's just this region of the sky, right? So they made it a weird blocky region that happens to encompass what we used to call that constellation. So in the same way, nebula, okay, that word was used a lot and it sort of is still used, but it doesn't really mean what it meant before. So once they knew these things were these distant objects, okay, then they started calling them something different because they really were something different. This is an elliptical galaxy called M87, again, 87th object in the Messier catalog there. And there is a little bit of detail here. You can see that bright spot right there. That's actually a really powerful jet that is being ejected from the center of that galaxy. And you may have seen pictures of this galaxy before that looks more like that, right? So just a few years ago, the Event Horizon Telescope collaboration produced the first picture, the first photograph of a black hole, a supermassive black hole, at the center of M87 here. So the black hole, this is sort of the event horizon. You can't really see the black hole, right? Because nothing escapes the black hole, including light. But there's a lot of material that goes whirling around this black hole, and as that material whirls around, it actually heats up and emits a lot of energy and a lot of radiation. And so it's that part that you're able to see in this. It is a bit of a difficult image to understand here in the sense that what you're seeing up here is part of the accretion disk that is back behind the black hole. But the light is coming up this way from that accretion disk, and the gravity is so strong it bends it toward you like this. So think of your eyeglasses here. It's not so surprising with our eyeglasses, right? You take a magnifying glass or my eyeglasses out in the bright sun, hey, you can focus it down to a nice sharp spot, right? Burn some leaves or something like that. Well, the same is sort of happening here. The light is bending because something is happening there, and it's because there's so much gravity. So it's a little bit hard to understand those images when you look at it at first glance there, but pretty spectacular. And most galaxies seem to have a supermassive black hole at their center, much like this one. This is one of the biggest. The Milky Way has a supermassive black hole. The mass of our black hole is something like 4 million times the mass of our sun. So it is huge, and we are able to watch things orbit it and still not actually see the black hole. But I digress. Let's go back home to the Milky Way. This is an image produced from data of the Milky Way. And the collaboration doing this is from the Gaia European Space Agency, the Gaia telescope. The Gaia telescope is actually measuring parallax. So back to the same idea that we were doing before. It's in orbit, and it is measuring distance, or measuring angles to stars, orientation of the telescope to stars, as it orbits the Earth, as the Earth orbits the Sun. So it's doing this 24 hours a day for more than 1 billion stars. So they've collected up more than 1 billion stars that they are able to determine using parallax where they are, three-dimensional location, as well as velocity for many of them. And from that, you know where all these things are. Hey, you pack it into a picture like this, and this is the Milky Way. But it is a flat picture of us looking at the Milky Way. That side wraps around to this side because they're looking in all directions, right? It's sort of like taking your panorama around like this, and then you look it on the flat distribution, right? Same sort of thing there. And you're folding it around this way, right? So here's over and here's under. And this stuff in here is the disk of the Milky Way. That's where we reside. There's all that gas and dust, and we can't see through there because there's too much gas and dust. We can't see the center, certainly not in optical wavelengths. You can see a bit more in some radio wavelengths and get actual measurements, which is how you see things going around the center of that black hole and so forth.
On this photo, Matt, can you point to where the black hole
In there someplace. Yeah, it's in. So this is the center of our galaxy, and it is so small compared to the scale there that I couldn't. I mean, it's going to be smaller than my laser dot by factors of thousands. I mean, the black hole is really tiny on that scale, which is amazing. Yeah. You can see on this photograph, thank you for stopping me though, there's the large Magellanic Cloud and there's the small Magellanic Cloud. So that's kind of cool. But all that dark stuff is just gas and dust that you can't see through, right? So they don't know where the stars are on the other side of that necessarily. There's a lot of good studies coming out of Gaia as well, where they are actually doing parallax and measuring the 3D shapes of some of these gas and dust clouds, which is pretty amazing. Yeah.
Where are we?
Oh, good question. We are out here looking at it. That's the best answer I can give you, right? So you're standing here, you're right there. So we are here, and it's there, right? That's the center. And but it's also wrapping around you, right? So those edges out there are actually behind you. So it is wrapped around you like this. So it would be better if I could take this image and stretch it all the way around the room like this, and up over the top. We might have hope of doing something like that in the planetarium, but in here it doesn't work. Great question, though, yeah. So here's maybe a better answer to your question, although in many ways it's a worse answer. Oops. So right there is the sun. There's a little label there that says the sun. Here's the center of the Milky Way. Our black hole is going to be in there. The Milky Way is a barred spiral. You have these arms coming off. We are right there. We're not even in one of the prominent barred spiral arms coming out there. We're just kind of in this funny little Orion spur of an arm coming off. I mean, it's kind of floating away from the rest of that arm. So we are not special in that Milky Way at all.
So when we're looking up, like we're in a dark spot, and we look up and we say, hey, there's the Milky Way.
Yeah.
Are we just seeing it, are we seeing all of that, or are we seeing that little spur?
You're seeing all of this band right there. Yeah, you're seeing all that. And depending on the time of year, so if you are out looking at it in the summertime here, right, you get a night and you can do astrophotography and get some beautiful images of these gas clouds and dust in the sky. If you're doing it in the wintertime, you're looking out on these other spots. You're looking, out from us in the wintertime is looking out here and looking out there. So you can still see it, but it's not nearly as impressive as toward the center because there's so many more stars in the center. Yeah. So this is not a photograph of the Milky Way. It is an artist's rendition of the Milky Way. And that's because there is no way possible for us to get off the surface of the Milky Way or get far enough away from the Milky Way to put it in one field of view. And if you were to be able to do that, it would be thousands and thousands and thousands of years before you would actually get the data to make that photograph. You would have to be 100,000 light years away, which means it's going to take 100,000 light years for that probe or that camera to send you the information for you to make the photograph. And you're going to be dead, and your kids are going to be dead, and so are your grandkids. So the best we can do is make a drawing of this, okay, with data. And we could spend a whole talk. In my astronomy class, we talk a lot about how we get the data for this sort of thing, right? And how can you construct this? You're inside the Milky Way. How can you know what it looks like? I'd be happy to chat with you sometime if you would like to know. All right, well, back to more stuff on galaxies and Hubble. So in 1929, Hubble was presenting a paper at the proceedings of the National Academy of Sciences. And he'd been studying a lot of galaxies, right? So because we now had this tool, the Cepheid variable stars, for measuring distances to galaxies, okay, they got to measure a whole bunch more of them. And they said, well, I wonder, some of these galaxies seem to be moving away from us. And they're moving away from us pretty quickly. Well, how quickly are they moving away? Well, so you plot this on a graph here, and on this axis here is how far, or this is how fast the galaxy is moving, and this is how far it is away from us. And what you find is, hey, when you have a galaxy that is really far away, it turns out it's also moving really fast. So the further away the galaxy is, or the cluster of galaxies, the faster it's moving away from you. Every direction you look. You look this way, you look this way, you look this way. The further away it is, the faster it's moving, but everything is moving away from us, which clearly puts us at the rightful center of the universe, which is where we want to be. Unfortunately, because of this relationship, you can work it out. It would be the same for every other galaxy that is looking out into space. Because things are moving further out, are moving away faster the further away you are, if you jump to the nearby galaxy, they're going to see the same thing. And so they can claim also, hey, everything's moving away from us. There is no center, I hate to tell you. So, if you're looking at this and say, well, how is that possible, though? Expanding, what is it expanding into? It's not expanding into anything. I mean, there's no brick wall out here, right, that it's going to knock down and move out into the space out here. And it's not empty space, because empty space is part of the universe. It's the universe that's expanding. So one common analogy that is given to help imagine that a little bit is, I intended to go buy a nice big balloon this week, but I didn't get to it. But imagine I have a balloon, and it's deflated. And I take a Sharpie, and I put dots all over this balloon, and they're equally spaced. And then I start blowing up this balloon. You would agree with me, the surface of that balloon is getting larger, right? Those dots are getting further away from one another. And the further away one dot is from another dot, the faster it's moving away from one another as you blow that up, right? And so it's not a perfect analogy because clearly this balloon is expanding into the space of the room. But if you confine yourself to saying, well, all that we have is the surface of the balloon, the surface is getting bigger and every object on that surface is moving away from every other object, and the further away you are, the faster it's going. Same thing is happening to the universe. But if we think of how many galaxies there are, this is a drawing of what we call the local group of galaxies. These are our nearby neighbors. Okay? Fortunately, we've placed the Milky Way right there at the center because we can. No one can stop us. I'm just going to do it. I'm putting us at the center. That's my coordinate system. It's a perfectly legitimate coordinate system. It's just not the center of the universe. But there's the Milky Way, and all the little dots that you see are other galaxies in our local group. There's about 60 to 100. And you're kind of wondering, well, can't you count better than that? The answer is no, we can't count better than that. But this is a zoomed-in view. There's the Milky Way. There's the Andromeda Galaxy we were talking about. There's the Triangulum Galaxy. And then all these other little dots are other little satellite galaxies. And we call them the local group because they are all gravitationally bound to one another. They're stuck. They're not getting farther away from us. We're all hanging out together. And in fact, some of these galaxies are coming closer to us. You want to talk about a collision? The Andromeda Galaxy and the Milky Way are on a collision course. It's going to happen in 5 billion years. But a lot of galaxies, right? So that's, 60 in the local group. Wow. Here's roughly the size of them. So the Andromeda Galaxy is kind of the behemoth in the neighborhood, and the Milky Way is about half the size of the Andromeda Galaxy, and the Triangulum Galaxy is about half the size of the Milky Way, and the Large Magellanic Cloud is not quite, or is a little more than half the size of that, and so on down. Those are just sort of the 6 biggest players in there, but there are a lot of other small galaxies in there as well. But 60-ish in our local group, all hanging out together, and we will sort of be stuck with one another for all of eternity. There are other galaxy clusters that we see, however. So the Hercules Galaxy Cluster, also known as Abell 2151. Again, Abell, it is a catalog that is named after the guy who put it together. And in this case, yes, a guy that put it together. If we were looking at these galaxies that you see here, so anything that doesn't have spikes on it is a galaxy. So the spike right there, that's a star, that's a star. But everything else in here, all the fuzzy patches, those are all galaxies. And so we're looking at 500 million light years away. There's about 200 of them in that group. Again, gravitationally bound to one another. They're stuck to each other, right? They're rotating around. They're not stationary, but they can't get away gravitationally. There's too much mass. For a sense of scale, the field of view, that's my abbreviation, field of view, 3/4 of a degree. Think of the moon. The moon is about half a degree. So this patch of sky is a little larger than the full moon would be. And you're seeing 200 galaxies.
Excuse me.
Yeah.
Sorry, how do you know that it's rotating around? Just because I'm trying to think of how long you have to watch those.
Yeah, very, very good question, absolutely. So the quick answer to you is the same way that the police officer is able to tell you how fast you're going with a radar gun, okay? The way it works is if you have this galaxy that's moving away from you, there are certain characteristic spectral lines. So hydrogen, for example, emits certain colors, and there's a lot of hydrogen in the universe. If it's moving away from you, it actually is shifted to a slightly different color. And so when you measure that color and you compare it to what it would be if it was stationary, and you can tell how fast it's moving. So that's the short answer to how we get most of those velocity pieces. And so you can look at these things and say, oh, these galaxies in that cluster, they all have roughly that same speed, but they're moving around in different ways. You're absolutely right. There's no way we could watch them because it takes billions of years. Yeah. Great question. All right. Majority of the galaxies here are spiral galaxies. If you blow up this region just for the sake of interest, you get something that looks like this, right? And I would argue you look at some of those and say, wow, it sure looks like some of those are interacting with one another, right? I mean, that one's kind of a funky one. And so, in fact, they are. This is another example of a galaxy cluster. This one is 54 million light years away, so 10 times as close. It doesn't show up as nicely in this because we have a somewhat larger field of view. We're looking at 8 degrees across here. But there are 2,000 galaxies in that cluster of galaxies, right, that are all stuck to one another, right? They're moving around, but they're not going to escape from one another. They're tied gravitationally to each other. And if you were to look at this through a small telescope, so take one of our telescopes down at the observatory, you might be able to discern 150, but it's going to be little dots like that that you're discerning, right? You'd be able to measure them, but it's not going to be spectacular. There's M87, that famous one that we have with the black hole. It's in that same cluster of galaxies. If you were to blow up that region, okay, you can see these tend to be a little bit more bluish in nature, okay? One of the really interesting facts about this particular galaxy cluster is they've discovered a lot of intergalactic stars. So there's so many galaxies interacting, and I'll show you a simulation that'll perhaps bring some of this to light. There's so many galaxies that are interacting that you can kick stars out of one galaxy, okay, and they just go flying across space. They're all on their own. They're not tied to the galaxy anymore as you have this interaction. And they've been able to see these. So as you start to wonder about, hey, can galaxies interact? You know, maybe these are passing ships in the night. The Hubble group put out this poster a number of years ago of some 60 or so interacting galaxies, okay? And we will look at a few of them. Here's just a zoomed in portion of that. So a few of these are more famous than the others. So this is ARP or ARP 148, 302. There was a gentleman in the late 50s, forget his first name, but the last name is ARP. He put together a catalog of peculiar galaxies, he called them, and a lot of them turn out to be interacting galaxies. But when you're first looking at these, you're like, man, that doesn't look like any well-defined structure, right? What is going on with that? So this up here, you have one galaxy that flew right through the center of another galaxy, and you end up with kind of a ring-type galaxy. So when we think of galaxies colliding here, so the image on the left is actually from a NASA supercomputer simulation, and the one on the right is actual photograph. And I'm going to show you a quick video clip that goes through the evolution of two spiral galaxies that are colliding with one another. And fortunately, with our computer technology, since we have a pretty good handle on physics these days, we're able to say, hey, this is how gravity works. All you have to do is set up 100 billion stars in this structure where they're rotating around as a spiral galaxy, and then you get another one going here, and you sort of clap them together and say, hey, let's see what happens when these things collide. And so that's what we're going to see here. It's only a couple minutes long. And what they're going to do is show you, and they'll do a stop animation. So here's our two galaxies, but we can also change our field of view. So that's why the star pattern is changing in the background, is we're changing our motion. So you saw, hey, this is one particular spot in the evolution, and there was a photograph that matched it. They continue the evolution process here, and then they pause and go around and say, hey, do we have any galaxies that look like this in that catalog? Hey, we sure do, right? So you let it continue on a little bit more, and you can stop it again and fly around, right? Because you can do that in a computer. And lo and behold, so many of those galaxies that you see out there just come right out of the simulation. It's just beautiful, right? And you have this advantage of having a supercomputer. You can make 4 billion years go by like that, right? And you have all this data. But really amazing. I mean, you wouldn't think that that was two spiral galaxies, but lo and behold, the evidence is pretty strong, especially when they do this over and over and find the same things happen. Pretty amazing. I think that's the last one. Maybe not. Yeah, there it is. So credits are there. If you want the links to that, I can get them to you. The end result of collisions like that of spiral galaxies, by the way, are large elliptical galaxies like M87. After 4 or 5 billion years and the collision is done, basically it loses all of its spiral structure. It stops forming stars, it gets yellow and red, and it just sort of fades away. Or, well, it still is big, so it can still put out a lot of light, but it is just aging, and no new star formation is going on with that either. Okay, we're not done with galaxies, though. Late 1980s into the 1990s, Margaret Geller, another fantastic female astronomer, she sort of got the idea of saying, hey, what would happen if we just looked out into this little orange slice of the universe, right? So you just take a little slice of the universe that's just thin, and you count the galaxies. You just say, well, we can measure how far away they are, so let's do this for a little slice, and let's see how, are they uniformly populated? Is it just this big distribution in three-dimensional space? And what you find is, no, it's not uniformly populated. You have these structures around there, right? So you have this clusters of galaxies like this, and then huge voids between them. And she wanted to map what is that distribution. In the end, after doing thousands and thousands of these, she sort of coined the term, it's like a soap bubble universe, right? So think of the big soap bubbles in your kitchen sink. There's these films, right, that have all of the soap, and then there's air between them. So for the universe here, we have these films of galaxies that are on those bubbles, and then you have huge voids in between there. And if we just go, you know, the previous one was 1,500 galaxies in one slice, 2,500 in another, 1,400 in another, And it sort of persists out to the distances that they were able to measure at the time. The Sloan Digital Sky Survey updated that in 2003, so this is an all-sky survey, basically automated all the time, where they're measuring distances to millions of galaxies, and this is the map that they put together, and it goes out further in distance, and what you can see is a lot of this filament-type structure persists, even out at those larger distances. And if you're wondering, hey, what's going on over here and over here, that's where the Milky Way is. You can't look through the Milky Way to see the galaxies on the other side, right? So you're sort of, if this is the plane of the Milky Way, you can look from here all the way over to here and around like this, but you're not going to count any galaxies if you're looking through the Milky Way. A more modern version, so this one I think is 2022, the Dark Energy Spectroscopic Instrument has gone out even further. They're looking out at 3 billion light years away from us, and the color coding does mean something, but it's not important for us. The filament structure is really what I want you to see there, that it persists out to those really vast distances. So, all right, we got lots of galaxies out there. You've probably seen an image like this, the Hubble Deep Field. I was talking earlier about how astronomers provide proposals to get time on different telescopes, right? And I think it was the late 1990s, maybe 1998, when a group of astronomers said, hey, let's actually take the Hubble Space Telescope and point it at the darkest patch of sky we can and just watch that patch of sky for about 11 days and do a time-exposed photograph and see what we see, right? And on the one hand, it's like, is that really a good use of time? I mean, if you don't see anything else, we could be studying something. But no one had done it before, so they did this sort of thing. And lo and behold, what they found was more than 10,000 galaxies, right? And the field of view on this, take the size of the moon, slice it up into 100 little tiny squares. That's the size that we're looking at there. The field of view is tiny, right? It is looking at a little tiny patch, and there's 10,000 galaxies in that patch. Unbelievable. If you go look at the James Webb Space Telescope photographs, it's even more astounding, right? They're looking back further. It is just crazy. So, can you, kind of sort of bringing us back to Earth here and also heading out to the observatory, can you see galaxies with the naked eye? You can, but it's going to be pretty hard. So you need some dark skies, and you need some good seeing, right? So the dark skies part of things, you've probably heard of dark sky parks, and there's an effort to try and make the valley a dark sky community, right? And so, if possible, when you have lights around your house, if you can replace the existing lights that are broadcasting lights with shaded lights like this that cast the light down, that really helps eliminate the light pollution that we have, and we're able to see things. And you can see stuff with the naked eye, which is great. So you need good seeing, you need good eyes. Those are not the same thing, it turns out. Good seeing is an astronomical term that basically means, hey, it's really a clear viewing night. If you have a turbulent night, like if you have a lot of wind up high and so forth, you are not going to have good seeing because there's too much going on in the atmosphere. So you want a calm, crisp, very cold night, okay, where it's nice and settled and everything is stable and you can see things. Then you can start to see some of these galaxies if you're experienced. So the Large Magellanic Cloud and Small Magellanic Cloud, you could see those even if you are not particularly strong-sighted, shall we say. The Andromeda Galaxy that we were talking about before, you can see it. I have seen it, but it is one of these things. You have to have dark skies, you have to know where it is, and you have to not look at it. Now that seems weird, doesn't it? So if it is over here, you want to look up this patch and just use your peripheral vision over here. So your peripheral vision is much more sensitive to very dim lights. And so you will see a fuzzy patch over here if you're looking off in this direction. And as soon as you try to see it, it's like gone, or just like that. You move back over, oh, there it is again. And then you look at it, and it's gone. So you can see that. I have not seen any others in this list, okay? This is a list that people will say, yeah, you can see pretty readily if you're good at it, up to 8 or so. There are some folks that have said they've seen up to 51 or something like that. And it's like a competition, right? I mean, that's what they like to do, and that's how they spend their time. And so I don't doubt that they can see it, but it's going to take some time and effort. And personally, there are other things I like to do with my time. So here's my list of references, books and traditional sort of papers and things like that on the left. A ton of websites, of course, as we would have on the right. If you want any of those, I'm happy to share them. And that's all I have for you tonight. So thank you. Question, Lisa?
I'm fascinated with the night sky.
Yeah.
And falling stars. What is it that we're seeing?
So a falling star is just a little piece of dust. It's going through the atmosphere and it's burning up. And that burning up process makes it bright for a really quick flash, depending upon when you're seeing it. So we talk about meteor showers, right? So really what's happening there is most of the time it was a comet that is going around the sun, and comets lose material all the time. But they're traveling around the sun, and that material keeps traveling around the sun, right? So that material from that comet is orbiting the sun like this, and we intersect that orbit at particular spots. And when we intersect that orbit, what we get is a meteor shower, because there's more than the average amount of dust that we're getting. But yeah, dust, micrometeorites and dust, we're getting those all the time. Even larger objects, right? So there was a 1 meter sized asteroid that was spotted a couple hours before it hit the atmosphere, and then was a nice fireball. This was just last week. Pretty good accomplishment, but yeah, fun. Any other questions? Yeah, Marty.
So there's no such thing as an average galaxy? Is
Good.
that an accurate statement?
Good question. There's a lot of common galaxies. So there's a lot of galaxies that have commonalities between them, and there's a lot of common galaxies. Variations in sizes, pretty much continuous, right? And then there's the big classifications are really spiral galaxies, but within spiral galaxies, you can get a, there's 3 types of spiral galaxies. Oh, well, if you look at finer, we actually categorize these seven types differently, right? So then it suddenly breaks apart into 7, and then pretty soon each of those is into 7. So it seems like it's kind of continuous, I would say. I'm not an expert in that, but so you have elliptical, you have spiral, you have lenticular, you have irregular galaxies, and then you have a whole bunch of other weird things too.
So in terms of numbers, though,
Yeah.
I think that one small slice that you showed
Yeah.
us, 10,000 galaxies.
This here, or
Yes.
yeah,
So 10,000 galaxies.
yeah.
There's no general statement that you could make about the number of stars per galaxy.
Not really, but so Milky Way is a pretty large galaxy. We have maybe 100 billion or 200 billion stars. The Andromeda Galaxy is bigger than that, so it has maybe 300 billion or 500 billion stars. Those are big. Generally speaking, things in the universe that are smaller are more numerous, right? So, for example, stars, we have more small stars than we have big stars. And the sun is a big-ish star, but it's by no means one of the biggest stars. But it's a lot bigger than a lot of the smaller ones. So the same thing, you have a lot of small galaxies. So if you remember the local group, we had 3 big galaxies in the local group, and then 50-some small galaxies, right? So there's more small ones than there are big ones. If you look at this image here, the yellowish ones tend to be the elliptical galaxies. The bluish ones, and some of them like this, okay, you can see some spiral arms in some of them, but those are active regions where there's forming stars and so forth. But also, the further back the more distant galaxies are also further back in time, right? So you can see more galaxies that are a long ways away from us because they didn't have time to collide with one another in the intervening 2 billion years that it took the light to actually get here. So the further back you look in time, and the James Webb Space Telescope is looking back at basically 13 billion light years or 13 billion years ago. Okay, well there's all these galaxies here, but they don't look like what we have today because there's been 13 billion years of evolution in between. Yeah.
So none of what we're looking at actually exists.
Right, even the sun, yes, and actually even us, but let's say we exist. But the sun is, when you see the sun, you're looking at light that's 8 minutes old. So yeah, the sun might not be there, who knows? Yeah.
If you could put a proposal together to take your 10 days on the telescope, do you have an idea what you would be looking for?
That's a good question. I've never thought about that. So no, I don't. I will qualify that with a couple of things. One is, I'm not a researcher, right? And so I like to get my current research by reading more concise versions of it. So like the journal Science, for example, has really good one-page summaries, right? And they send the Journal of Science out to, mostly scientists are reading it, right? But I'm not an expert in that, but I can understand what's going on there. So in answer to your question, yeah, I don't know. There's so many great questions out there in the universe left to ask. I'd have to think long and hard about that one. Yeah. Yeah.
If you were to ever have to move galaxies,
Yeah.
what type of galaxy?
Good question. So what type, if we ever had to move galaxies, what type of galaxy would we have to go to? So I guess my first answer to you would be, we probably can't get there, so we should never make the trip. Where we might be able to get to in the future with technology would be to neighboring stars, right? So if I wanted to go someplace, I would probably personally want to go someplace where I know there's a planet that has certain things and certain chemical elements that could support life, right? And so that's a whole nother field of what we're looking at in astronomy, exoplanets, trying to discover planets around other stars. And we have a catalog of more than 5,000 of those these days, some of which seem to have Earth-like characteristics. And so that's probably the next leap, rather than going all the way to some other galaxy, would be, okay, but even those stars are really far away, right? So if you have the nearest stars are 4 light years away, and we can't travel anywhere near the speed of light yet. If someone figures out how to do that, okay, even if they figure out how to go almost the speed of light, it's going to take you 4 years to get to the nearest star. It's going to take some time. But yeah, it's really interesting and fun to ponder things like that. Yeah. Anything else? Yeah.
I'm trying to formulate my question here to make sense. So, when you talk about the local group of galaxies,
Yeah.
and then I was seeing some data, even the larger group of galaxies,
Yeah.
and they seem to be moving towards something.
Yeah, the great attractor.
Right?
Yeah.
And so when we start talking about expanding, and then we're talking about things moving away,
Yeah.
it sort of makes counterintuitive sense that
Yeah.
we're moving towards that.
You're absolutely right. It's a great observation. So the question is, when we talk about the local group, okay, the local group is stuck together. We're not moving away from those. But I said earlier, hey, when we look out, galaxies are moving out away from us in every direction that we look. And it is true, but then if you also map the general velocities, there is a region where many galaxies and many groups of galaxies in our region of the universe, whatever that means, generally are moving in this one direction, right? So the great attractor. But if you look out at larger scales than that, everything is moving away. So we could look at these pieces here, right? So when you look out further, if this is us here and you're looking out to these, the velocities that you calculate and measure for these are faster than the velocities that you measure for these that are closer by and so forth. But you're absolutely right. It does get to be a little bit mind-bending trying to pull all these things together. Because, yeah, there are some things that we don't know. What is this big thing over here? Why are all these galaxies and groups of galaxies moving in this direction? But on an even larger scale than that, everything is moving away. Yeah, good question. And I tend to gloss over a lot of these things, like in public lectures, because I could end up spending 3 days talking about some particular little aspect sometimes. Yeah?
Is it even physically possible for humans to create anything that can even go close to light speed?
So is it possible for humans to create anything that can go close to light speed? Yes, we can, and we do it all the time in a particle accelerator. So you can take electrons or protons that are sitting here stationary, and we can make them go really, really fast. So the Large Hadron Collider has things that has protons that are going essentially the speed of light, not quite, but 0.999.
I meant for like traveling, like trying to get to new planets.
Yes, of course you did, but I wanted to be able to see, yes, we can do it, right? The other answer to your question is no, we can't. We don't even come close. So we have the Pioneer and the Voyager spacecrafts, right? These were launched in the 70s and 80s, leaving the solar system, right? But it has taken 50 years for them to get that far. Yeah, we don't. They're moving as fast as anything we've done. So no, we can't. It takes so much energy, it turns out. Yeah.
So even if there was like life on like other planets that we could see that are moving away from us,
Yeah.
what if they see us moving away from them?
Yes, they would see us moving away from them. Yeah. So, if we're talking about things out in other galaxies, but if we're talking about our galaxy, okay, which there are, take 100 billion stars in our galaxy, each star has, on average, at least one planet. That's not to say every star has a planet, but each star on average would have at least one planet, probably more. So we could have planets that are not necessarily moving away from us. Some of them could be moving toward us because we actually have stars that are passing by one another when we look at the night sky in the Milky Way. Yeah. But again, the distances are really far. So if you think about communication, you can use radio waves to communicate. You turn on the radio. It is not a sound wave. It is an electromagnetic wave, just like the lights overhead are. And it's traveling at the speed of light. But we've only had radios for something like 100 years. right? Or 120 years. All right, so the sphere of expansion of the radio waves that we've generated is only out 100 light years, right? And that's not a very big corner of our Milky Way, much less the universe. All right, I need to go set up telescopes and so forth, so we're going to call it a day there. Thank you for coming. Really appreciate it. Enjoyed it a lot. And please, if you have time, stop by for 5 minutes and see some stuff through the telescopes. So.